Okay guys, we're gonna try to keep this video to 15 minutes or less. Let's see how I do. So we ended class today, right, by talking about the difference quotient as we see here, okay? And we talked about taking the limit of the difference quotient, i.e. taking the slope of a secant line where the 2 points are literally on top of each other, so that the denominator in your slope formula, which is change in x, right? Usually that's change in x, is equal to 0. So if you eliminate the limit as h approaches 0 part and think about what the difference quotient would be if h were 0, you couldn't take it, right? You couldn't find the slope at a singular point. But if we use a limit, the idea of a limit as like what is this slope approaching as the difference in the denominator, the difference in the 2x coordinates is 0, we can actually approach what that slope at a singular point would be. And that's what the derivative is. It's the limit of the difference quotient as h, or the change in x, goes to 0. Okay, we call that the derivative, as I said. We call it the derivative. You're going to hear it used a lot. We're going to learn some shortcuts for taking it, but for now, our derivative is going to be defined as the limit of the difference quotient as h approaches 0, and we're going to call that the limit definition of the derivative. Okay, so let's actually see how it's going to be used. So example 1 here, it says using the limit definition of the derivative, find the slope of the function. Okay, I want you to think of slope. When you see slope, okay, think, okay, instantaneous rate of change. That's what slope is. Usually it's an average rate of change when we're finding the slope between 2 points, but when we do it at 1 point, it's the instantaneous rate of change. Okay, so we need to find the slope or the instantaneous rate of change, okay, of the function 2x squared at x equals 3. And the only way we know to do it now is to actually take the limit definition of the derivative of 2x squared and try to solve that. So step 1, right? Let's actually write out the limit definition of the derivative with that function 2x squared. So if you remember, it was the limit as h approaches 0 of f of x plus h. Well, f of x in this case is 2x squared. So instead of putting in x, okay, I'm going to put in x plus h. So it's going to be 2x plus h squared, okay, minus 2x squared. So it's f of x plus h minus f of x all over, okay, h. Now if we try to solve this limit, we can't solve it, right? Because h is 0. So we have to find a way to simplify it. So let's see what we can do. Any thoughts? Well, we have x plus h squared. So what if we try to FOIL that? Maybe some things will cancel out, and we'll go from there. So let's rewrite it as the limit as h approaches 0 of 2, and we're going to FOIL this out. X squared, that's the first terms, plus 2xh, that's the two middle terms, plus h squared minus 2x squared all over h. Again, I'm trying to solve this limit, and the only way I'm going to be able to solve it is to eliminate that h. So I'm hoping maybe I'll be able to factor out an h in the numerator, and I'll be able to cancel out the h in the denominator. So, looks like I've folded it. Let's see if we can maybe simplify a little bit, combine some terms. So the limit as h approaches 0. If I distribute that 2 in, we get 2x squared plus 4xh plus 2h squared all minus 2x squared all over h. Well, one of the nice things about this is that what happens to the 2x squareds? Well, I have a positive 2x squared and a minus 2x squared, so those cancel out. What I have left is 4xh and 2h squared. So I can factor an h out of both, so the limit as h approaches 0 of h, parentheses, and what I have left is 4x plus 2h all over h. Okay, and you can see what happens now. Those h's I went through all of that jazz, all that combining and everything, just to cancel out those h's, which allows me to restate my limit. Okay, I come over here as the limit as h approaches 0 of 4x plus 2h. Okay, now am I allowed to solve that limit? Now can I plug in 0 for h? I can. So that gives me to a limit of 4x. Okay. Now I want to know that instantaneous rate of change at 3. All we're going to do is plug in 3 for h. Excuse me, plug in 3 for x. So the way we notate this, okay, is something like f prime of 3. F prime just means derivative. It's the notation for derivative. So the derivative at 3, we're going to plug into that function 4x, so 4 times 3. That equals 12. 12 represents the instantaneous rate of change of 2x squared at x equals 3. Okay, another way to say it, it's the slope of the tangent line to 2x squared at x equals 3. Okay, so here's what I want you to do. I want to take a look at example 2. Actually, no, I take that back. Before we do that, I want to introduce another way to talk about the derivative. So again, the derivative, or the tangent line to a curve at any point, is just basically the limit of a slope formula. And another slope formula we have is what we call the f of x minus f of a version. So if we look at this, I want to know what is the limit as we approach a, okay, of this slope formula right here, which is f of x minus f of a all over x minus a. That's a slope formula. It's change in y over change in x, but you can see if you plug in a, you're going to get something over 0, which we cannot do. So this is like an alternative, okay, alternative formula for slope. Another one, okay, for slope, and if we take its limit, it's also the formula for the derivative. Okay, so let's actually take a look at 2 examples real quick, and can see why this version, what we call the x minus a version, is a little bit easier at certain times to actually find the derivative. So what I want you to do is let's go to example 2 and take a look at f of x equals negative x squared plus 15x. And what I want you to do is to pause the video and see if you can, using the x plus h version, to find me the slope of the tangent line at 6. So I'll maybe set it up for you, and then I want you to pause the video and see if you can find it. So what I want to do on the left side here is find the limit as h approaches 0 of f of x plus h minus f of x over h of the function, okay, negative x squared plus 15x. And then I want you to find that slope at 6. So if we set that up, it's going to be the limit as h approaches 0 of negative x, negative x plus h squared plus 15x plus h all minus negative x squared plus 15x all over h. So I want you to try to do what we just did a second ago and combine that, factor, simplify until you can actually answer the limit. So you can actually plug in h and get a value for the limit. And then once you have a value, a generalized value for that limit or a generalized derivative, I want you to plug in 6 and see if you can get the value. And once we do that, we'll jump into the x minus a version. So pause the video and see if you can do that. Okay, so hopefully you're able to do it. I'm going to quickly run through it. If you want to fast forward a little bit to the end of me working on this, you may do so to see if you got the right answer. So that would be my first step. Second step, right, as we do this, okay, we're going to distribute. So we get negative parentheses x squared plus 2x h plus h squared plus 15x plus 15h plus x squared minus 15x. I'm distributing that negative in, and it's going to be all over h. Okay, and we're going to continue to distribute. So step 3, the limit as h approaches 0 of negative x squared minus 2xh minus h squared plus 15x plus 15h plus x squared minus 15x. You can see it's very easy to make a mistake if you're not being careful. Step 4, let's see what crosses out. Looks like my x squareds, they cross out. Looks like my x's cross out. And what I'm left with is a limit as h approaches 0 of negative 2xh plus 15h minus h squared all over h. Okay, the idea here again is we want to cancel out that h in the denominator so we can factor out an h in the numerator. It looks like in this case the limit as h approaches 0 of h times negative 2x plus 15h, or excuse me, not 15h. Let me erase that. Plus 15, okay, minus h all over h. Now those h's cancel out, and we are left with, in step 6, the limit as h approaches 0 of negative 2x plus 15 minus h. If you plug in 0 for h now, the limit does work, and we get negative 2x plus 15. That's your generalized slope formula, or the derivative, right? It's also just called the derivative. Okay, if we find the derivative. So if I want to know the derivative now at 6, f prime of 6, or the slope of the tangent line at 6, is going to be negative 2 times 6 plus 15, which equals 3. That is a very long way, and a long process to find that value of 3. So let me show you the other way, using x minus a, and then we're going to call it quits on the video. Okay? So let's use that version. That was the, right, it was the limit as x approaches a, which a in this case is 6. So step 1, we're going to say the limit as x approaches 6 of f of x, so just the function. So in this case, the function is going to be negative x squared plus 15x minus f of a. So it's basically the value of the function at a, which in this case is 6. So minus, and then I'm going to plug in negative 6 squared, negative positive 6 squared plus 15 times 6. I'm basically plugging 6 into the f of x, right? So you can see that all there in the parentheses, all over x minus 6. And you can see if you try to solve this limit here, right, and you plug in 6, you're going to get a 0 in the denominator. So much like we did in the x plus h version, we're going to have to simplify the numerator, see if maybe we can do some factoring and we can cancel out that x minus 6 in the denominator. So let's try this again. The limit as x approaches 6. Okay, let's see if we can simplify this. Negative x squared plus 15x. And if we simplify all that arithmetic there, negative 6 squared plus 15 times 6, okay, we get minus, okay, a 54 all over x minus 6. Well, if we do some more factoring here, we have the limit as x approaches 6 of negative x squared minus 15x plus 54. That's over x minus 6. So it's still some work using this method, but you'll see what happens here. It's a little bit quicker. So we get the limit as x approaches 6 of negative. If we factor the numerator now, we get x minus 9 and x minus 6 all over x minus 6. What's great about this, x minus 6's cancel out, and I can rewrite this simplified limit as the limit as x approaches 6 of negative x minus 9. Now, can I plug in 6? I can. Okay, I get negative 6 minus 9, which is negative 3, or positive 3. So what does this mean? It means that f prime of 6 equals 3. Okay, so you can see both methods got us the same version, or same value. Okay, what's one of the benefits of doing the x minus a version is that sometimes this method's quicker. Sometimes it's quicker. And you're gonna have to use a little intuition as you do some more practice, the better you'll get at it. You'll have to use some intuition to figure out which one's the best. Okay, so it's sometimes quicker, but one of the advantages, and probably what makes the x plus h version the best version, is that you get at the end, you can see the negative 2x plus 15, you get this generalized slope formula that you can plug in any value. So if I wanted to know the slope, for example, at 10, I could just do f prime of 10 and plug it into this generalized formula. I know I'm running out of room. Negative 2x plus 15, and I get negative 5. So I can find the slope at any point using this generalized formula, negative 2x plus 15. Using this version over here, okay, you don't get a generalized formula. You have to go through all that process, or that whole process, for every single point you're trying to find it at. So I would say certainly if you're trying to find the slope at multiple points on the same function, you definitely want to use the x plus h version. If you're finding it at one singular point, then perhaps the x minus a version is better. All right, this is a lot to throw at you, so all I want you to do, okay, is a couple problems for homework. Okay, what I want you to do is problem 1, okay, problem 1 here, okay, and this one I want you to use the x plus h version. And in problem 2, I want you to use the x minus a. Okay, use the x minus a version. Okay, so hopefully that'll take you, I don't know, 10, 15 minutes. I know the video ran a little bit long here. Do your best, forget the rest, and we'll talk about everything tomorrow.